Hello everybody and welcome to our video on related rates. So this is going to be a big applications section. We're going to see a lot of use of applying these concepts of derivatives to various problems. But of course we should ask ourselves, what are related rates? Well, those are just equations that relate various derivatives to one another. So with these problems, these word problems, there's the method that you're going to use is every problem is going to be quite a bit different because you're applying these to different circumstances, but there's sort of an overall set of guidelines for how to strategically go through these problems and avoid making common mistakes. So, method. First, read carefully. Read the whole problem. Typically, I would suggest read it twice. So, first I would say read it a little bit more quickly, get the big picture, and then read it again more carefully and slowly and start writing out all your details. 2, make a picture. The vast majority of these problems are going to require some sort of geometric analysis of the shapes involved in them. So drawing that picture is going to help you relate the components to each other appropriately. Generally speaking, it's very difficult for students to do well in these problems if they try to skip the process of drawing the picture. There might be some easy problems where you can get away with it, but if you have a bad habit on the easy problems, then when you get to the hard problems and you really need it, you're more likely to make mistakes. So try to just make sure you always draw some sort of picture if you can. 3, you need to decide on notation. So it just means pick your variables and how you're going to label them. What are you going to label each thing? And then once you've done that, express the given information in the problem and the required rate in terms of derivatives. So typically these problems are going to be asking you to solve for a particular rate of change. So we just want to write down in terms of the notation, which things are we solving for, what do we want, what do we have, etc. Now use the information you have to write an equation that relates the various quantities. Once you have that equation, you differentiate it. Now you will have related rates to one another. And then you can substitute your given information to solve for the unknown rate. So let's try to demonstrate this process for the first problem. So read carefully. So example 1, the length of a rectangle is increasing at a rate of 8 centimeters per second. And its width at a rate of 3 centimeters per second. When the length is 20 centimeters and the width is 10 centimeters, how fast is the area of the rectangle increasing? Okay, hey, that's kind of a lot. Let's go a little slower, and maybe we might even read it the second time while drawing our picture. So we're talking about a rectangle here. So let's just draw our rectangle. Okay. So the length of the rectangle is increasing at 8 centimeters per second. Well, let's call the length L. Then the increasing rate would be dl dt. All right? So that's dl dt. Oh, so that's 8 centimeters per second. So the length of the rectangle is increasing at a rate of 8 centimeters per second. All right, so we've decided on some of our notation as we're making our picture. So sometimes you won't do these in the exact order, or you might do kind of multiple parts at once. That's perfectly fine. Its width is increasing at a rate of 3 centimeters per second. Well, let's call the width W. And then dw dt would be 3 centimeters per second. So the length at the particular time is 20 centimeters, and the width is 10 centimeters. So we'd say that this is 20 centimeters at the instant in time that we're concerned with, and the width is 10 centimeters. How fast is the area of the rectangle increasing? So in other words, what do I want? I want the derivative of the area with respect to time. Okay, so one other thing I want to point out. So we're going to need to find equations for the area. it is really, really important that you do not substitute numerical values in until after you have completed the differentiation. Because these values typically are not constants, they're changing, and derivatives are rates of change. So if you plug into your area formula with 20 and 10 before you differentiate, that will be treating the length and width as if they are fixed and that they do not have a rate of change. And that will make your derivative for area incorrect. So because these things are changing, when we are taking our derivatives, we have to keep them as variables and only plug in at the very end of the process. So with that being said, well, what is our area? Okay, so what have we done? We've read carefully, boom. We made a picture, boom. We decided on notation, boom. We expressed the given information and required rates in terms of derivatives, boom. We write an equation that relates the various quantities. A equals length times width. Done. Now we differentiate. But we want the derivative with respect to time here. So when I take this derivative with respect to time of L times W, I have to apply the product rule. And so I get dL dt times W plus L times dW dt. So we differentiated. And now there's only one piece of this puzzle left, which is substitute the information in. Now we've got our formula for dA dt. So now we're going to take it at L equals 20 and W equals 10. So at that particular moment in time, dA dt is going to be dL dt, that's 8 times W, which is 10, plus L, which is 20, times dW dt, which is 3. And of course, this is the rate of change of area, so we could track our variables, or our units, I should say, but it's of course going to be centimeters squared per second. So this is 80 plus 60, that's 140 centimeters squared per second. Okay, that's it for our first example. So again, these are the key steps that you need to do in these problems. Read the problem carefully, make a picture, pick out what notation you're going to use for your variables and rates of change, express all the information in terms of that notation, write an equation, differentiate, solve. All right, let's move on. Okay, two cars start moving from the same point. One travels south at 50 miles per hour, and the other east at 30 miles per hour. At what rate is their distance apart increasing 2 hours later? Okay, so we'll put the starting point here. I'll just call it S. So one is going 50 miles per hour, and the other is going 30 miles per hour. So we need labels for these. How about we'll call this one Y and this one X. And so what do we have so far information-wise? The one traveling south, dy dt, is 50 miles per hour. And the one traveling east, dx dt, is 30 miles per hour. So we've created most of our picture, but what do we want? Well, let's label this side Z. But what we want is the distance apart between the two, and that's Z. So what we want is dz dt. Now we're also going to need the total distance traveled in the X and Y direction. So for X, the total distance after 2 hours is going to be 60 miles. And for Y, the total distance is going to be 100 miles. Okay, so what have we done? We've drawn a picture. We read the problem. We've drawn a picture. We've come up with notation. We've labeled our picture. Now we need to find an equation to relate our components, but this is a right triangle, right? One of these was heading south, the other was heading east. It's a right triangle, and so we know that z squared will equal x squared plus y squared. Now I could solve this for z explicitly, but then I'll have a square root, and then when I take my derivatives, I'll have a chain rule. Actually, it's going to become a lot more complicated if we do that. But instead, what I can do is take my derivative with respect to both sides of the equation, not just like with any other implicit differentiation problem. And remember, all of these variables are functions of time. They're all changing with respect to time. So we have to apply the chain rule for each of these. I get 2z times dz dt equals 2x dx dt plus 2y dy dt. Now I'm going to divide everything by 2. And then I'm going to divide all of that by z, because what do I want? I want dz dt, so I'm just solving it algebraically. So dz dt equals x dx dt plus y dy dt divided by z. Okay, so I know what x is at the given time I'm concerned with. I know what y is. I know what dx dt and dy dt are. But I'm missing this piece x. But that's okay, because again, this is a right triangle. So I know that z squared equals 100 squared plus 60 squared. So z is the square root of 10,000 plus 3,600. And I'll just rewrite that as 13,600. So finally, to take all of this information, reach a conclusion, we see that dz dt is x, which is 60, times dx dt, which is 30, plus y, which is 100, times dy dt, which is 50, all over the square root of 13,600. I'm going to clean this up a little bit, but I'm not going to plug this in for a decimal, and it's not too much point in that. You can plug it into a calculator yourself to see the decimal response if you'd like. But here we've got 60 times 30. 6 times 3, that's 18, and times 100, 1,800 plus 5,000. So that's going to be 6,800 divided by the cubed root, or the squared root, I mean, of 13,600. And of course, we're talking about rate of change of this distance here. This is miles per hour. Okay, so that's going to be it for our second example here. Let's go ahead and move along. Example number 3. The radius of a sphere is increasing at a rate of 4 millimeters per second. How fast is the volume increasing when the diameter is 80 millimeters per second? So we have a little bit of a trick here, and this is one of the many things that you have to look out for. We're talking about the radius of a sphere, dr dt. So again, we've read the problem. Let's draw a picture. So first of all, we're talking about a sphere, and its radius r. Okay, I've drawn a circle here because I'm bad at drawing spheres. Here, I'll do a little. Yeah, that's awful. All right, that's my sphere. Great job, me. All right, the radius of a sphere is increasing at 4 millimeters per second. So I've been given dr dt. Okay, that makes sense. But here, the diameter is 80 millimeters. Well, if I'm trying to, figure out the volume of this thing, well, first of all, what is the volume? In general, it's 4/3 pi r cubed, right? But I need the radius, and I've been given the diameter. But the radius is just half of the diameter. Okay, so we've picked variables, we've picked notation, we've expressed our information in terms of that notation. Now, what are we asking for? How fast is the volume increasing? So we want dv dt. Okay, well, we have everything we need then. So first, let's start by taking our derivative. So we've got v equals 4/3 pi r cubed. So dv dt is 4/3 pi times 3r squared times dr dt. Here's the key. We've got to remember we're taking our derivative with respect to t. And so we have to apply the chain rule to r, which is changing with respect to t. The 3/3 cancels, and we get 4 pi r squared dr dt. So that means at the time when r is equal to 40, our dv dt is going to be equal to 4 pi times 40 squared times 4. And again, this is the rate of change of the volume. So we're talking about millimeters cubed per second. So 4 times 4 is 16. So we'll say 16 times pi times 40 squared, which is going to be 1600. And that gives me 25,600 times pi millimeters cubed per second. I said 25,600, I'm pretty sure, but I did not write it. Let's fix that 6 there. 25,600 times pi millimeters cubed per second. Okay, that's it for example 3. Now, so far, I think the examples we've done have been relatively easy. This one's going to be quite a bit trickier. So the last couple, and I really just read them one time and kind of tackled it. So we're going to read this one twice for sure. Water is leaking out of an inverted conical tank at a rate of 10,000 centimeters cubed per minute, and at the same time, water is being pumped into the tank at a constant rate. The tank has height 6 meters and diameter at the top of 4 meters. If the water level is rising at a rate of 20 centimeters per minute, when the height of the water is 2 meters, find the rate at which water is being pumped into the tank. Okay, so we have a little bit of a problem right off the bat that I notice as I'm reading this, which is that we are really mixing units here. We've got centimeters cubed per minute, we've got meters, very complicated. So here's the thing. I could convert centimeters to meters or vice versa, but we have to be really careful when we have cubed units because it's not as simple as just multiplying by a regular conversion factor because it's been cubed in the process. So it's easier to convert any units that are not raised to a power, right? So we're going to convert all of our meters right off the bat, and then we're going to read this again slowly and go from there. So each meter is 100 centimeters. So 6 meters, 600 centimeters. And the diameter at the top is 4 meters. That's 400 centimeters. And the height of the water at the given time we're concerned with, that'll be 200 centimeters. And I know they're talking about a conical tank. So I'm going to draw this thing and then we're going to read this again. So we've got a conical tank. And it's got like a hole at the bottom of it. It's leaking water out. So there's water coming out and there's water coming in. Okay, and what do we know? Well, we know that the diameter at the top is 4 meters. That means that the radius at the top is 200 centimeters. And likewise, the height at the top is 600 centimeters. Okay, so let's read it out again, and we will start writing down, notating some information here as we go. Water is leaking out of an inverted conical tank at a rate of 10,000 centimeters cubed per minute. Okay, so there's a change in volume, and we're going to call this dV out because it's not the total change in volume. This is just how much is going out, and that's going to be 10,000 centimeters cubed per minute. But you might want to think of this as a negative, right? It's the rate of change is a negative here because we're losing volume from the cone. Now, the same time, water is being pumped into the tank at a constant rate. So there's this dVn. It doesn't say what it is. Okay. The tank has height 600 centimeters and diameter 400 centimeters at the top. The water level is rising at a rate of 20 centimeters per minute when the height is 2 meters or 200 centimeters. Find the rate at which water is being pumped into the tank. Okay, so let's parse that last bit here a little bit. So we're looking at the moment when the height of the water in the tank is 200 centimeters. And what we're saying is that at this moment, the change in height, the water level, is 20 centimeters per minute. What do we want to find? The rate at which water is being pumped into the tank. So we want dV in dt. Okay, well, I'm going to have to start by thinking about the volume itself. How is the volume changing altogether? So we got a little bit of trickiness here. So the first thing we're going to have to realize is that we have two variables involved here. So let's write our equation. So we've labeled all of the things that we needed to label, but our volume of a cylinder is 1/3 the area of the base, which in this case, well, we're looking at the volume of this water in the cone. So the base is whatever that radius is squared times pi. So pi r squared times the height. Okay, so that's a problem because we have two variables here. Now, technically, we could take this derivative with the product rule and deal with both variables, but that actually will become a bit more complicated. Instead, what we're going to do is take a look at this picture again and notice something that's being implied here. So the overall height of this thing is 600. The width is 200. And then when I look at this little slice where the water level is, this is R and this is H. Now these are similar triangles. They share the same base angles. And then they both have right angles, which means these other angles are also congruent. And one thing we know from geometry is that the ratio of corresponding sides in a triangle is always equal. Of similar triangles, I should say, is always equal. So R divided by H should be equal to 200 divided by 600. So R over H is 1/3. This allows me to substitute one of my variables in place of the other. Now, since I already know what dH dt is, I'd like to write this whole volume function in terms of H. So I need to replace R. So I'm going to rewrite R as H over 3. Now I can plug that in, and my volume becomes 1/3 pi times H over 3 squared times h. And now we just do a little bit of cleanup. This becomes pi h cubed over 3 times 3 squared, which is 27. So now when I take my derivative of this volume with respect to time, I'm going to get pi times 3h squared over 27. And I have to apply the chain rule, so I get times dh dt. Now 3 over 27 is 1/9. Pi h squared over 9 times dh dt. Okay, so now we can finally consider, at the moment, that h is equal to 200. So once we plug that in, we get dv dt equals pi times 200 squared over 9 times dh dt, which is 20. So let's see, that should be 200 squared. So that's going to be 4 with 4 zeros, right? So 200 squared is 40,000 times 20 over 9. So that's going to give me pi times 800,000 divided by 9. We'll leave that for now. Okay, so that's dv dt, but now we got to go back and remember, hey, what we were asked for was not dv dt, it was dvn dt. So what do we know? We know that the total rate of change is the amount going in minus the amount going out, which was 10,000. So if I rearrange this, dv in dt should be equal to dv dt plus 10,000. And so if I take this number and I sum 10,000, and I'm just going to go ahead and throw that one into a calculator. I've actually thrown it into the calculator ahead of time. That's going to be 289,253 centimeters cubed per minute. All right, so that's definitely a bit of a more challenging problem, but the same basic process applies. First, read carefully, draw a picture, label the pieces you're working with, figure out what derivative you're looking for, write an equation, take the derivative, and apply it. All right, so let's take a look at this example, number 5 here. Now, sometimes you'll be given the equations you need for a related rates problem explicitly. And in that case, it actually just makes the problem a little bit easier because you don't have to figure them out from the context of the problem. So we're going to do a quick example of one of those. Here we've got if x squared plus y squared plus z squared equals 16, and dx dt equals 10, and dy dt equals 3, find dz dt when x, y, and z, the point is 3 to the square root of 3. So this is actually the equation for a sphere, and this is just a point on that sphere. And these are the speeds at which the particle at that point is moving along the sphere. Okay, so let's start by taking a derivative. So we'll take the derivative with respect to time of both sides of our equation. The derivative of 16, it's nice and simple. That's just 0. So here we've got the derivative of x squared with respect to t. So that's going to give us 2x times dx dt plus, and then for y squared, we get 2y dy dt plus 2z dz dt. And of course, we can divide everything by 2 here, and then we get x dx dt plus y dy dt plus z dz dt equals 0. Now, what we want to solve for is dz dt, and we know values for everything else, so let's just go ahead and plug those other values in, then we'll do the algebraic solving at that point. So x is going to be 3. dx dt was given as 10. Y is 2. dy dt is 3. Z is the square root of 3. And dz dt is what we're solving for. So this is all still going to be equal to 0. 3 times 10 is 30, plus 2 times 3 is 6. That's 30 plus 6 is 36, plus the square root of 3 dz dt equals 0. And now we just solve for dz dt algebraically. I subtract the 36, get the square root of 3 times dz dt equals negative 36. And now we'll divide by the square root of 3. And we get dz dt equals negative 36 divided by the square root of 3. Okay, now let's move on to a more challenging problem. So this one's pretty tough. A street light is mounted at the top of a 15-foot tall pole. A man 6 feet tall walks away from the pole with a speed of 5 feet per second along a straight path. How fast is the tip of his shadow moving when he is 40 feet from the pole? Okay, so we have to draw a picture for this, and we have to figure out how to label the picture. I'm just going to tell you that, when you're working on a problem like this on your own, there is a good chance that the first way you try to label this picture and set it up just isn't going to work out in a useful way, and then you got to take another approach. That's perfectly fine and perfectly normal. But I'm going to go ahead and jump into a setup for this that I know is going to work out for us. So we are going to imagine a street light right here. This is our 15-foot tall pole. And somewhere down the way is a person who's about 6 feet tall. And if we'll put the ground here on the bottom, as we usually do with the ground, And we imagine the light coming from this pole is going to eventually cross paths with this guy's head, and that's going to cast his shadow on the ground there. So of course we've got 2 right triangles here. The right triangle with the man's position formed vertically, and the right triangle where the street light is mounted on that pole. And what do I want? I know that the person is moving away from the pole with a certain speed, so let's label the distance from the pole. That's x. And we also have to figure out something to do with this point where the shadow hits the ground, the top of his shadow hits the ground. So let's call the distance from him to that point y. So in this case, what do we know? We know that dx dt is 5 feet per second. So now what we've got to figure out is a way to, what do we want to know? Sorry, I should have said that first. We want to know. Now this one's a little different than other problems we've done. So here, what I want to know, because I'm using 2 separate variables, I want to know the rate of change of the sum of x and y, because the actual rate of change of this point is the combination of these 2 lengths put together. So we want to know the rate of change with respect to time of x plus y. So now what I need to figure out is, okay, well, how can I relate x and y together? Well, we've got two similar triangles here, right? So we've got a base angle that's shared by both triangles. They're both right triangles. That means that these angles will also be congruent. And so if all three angles are congruent, these are similar triangles. And we know that the ratio of sides of similar triangles are equal. So let's go ahead and write that ratio out. So we can write this as y over 6. That's this side over this side. And then for the large triangle, our bottom side here is x plus y divided by 15. Okay, so now I could multiply this 6 across, and I could write, well, let's see, yeah, that'll, and then I can multiply the 15 across, so we'll get 15y equals 6x plus 6y. I'll subtract that 6y. That gives me 9y equals 6x. And if I divide by 9, I get y equals 2x over 3. So normally I would have to substitute this in to some other expression, which I sort of do have to do here, but here it's a little more direct actually, because I'm just trying to calculate this derivative, dx plus y dt, but the only information I have is dx dt. So since I can rewrite y in terms of x here, this becomes d dt of x plus 2x over 3. If I have 1x plus 2/3 of x, that's going to be 5/3 of x. And so when I take the derivative, I'll get 5/3 times the derivative of x with respect to t. And I know that that derivative is 5, so this is 5/3 times 5, which is 25/3 feet per second. All right, well, that's it for this one. Thank you for watching.